Think about what happens when you turn on the kitchen tap. Water immediately bursts out. When you flip a switch on the wall, the room fills with light. Both actions rely on the exact same physical principle. Water needs a pump to create the pressure that forces it through a pipe. In a wire, a battery acts as that pump. It creates an electrical pressure, which we call voltage. Once you have that pressure, tiny charged particles begin moving through the wire, behaving exactly like water flowing down a pipe. That physical movement of particles is electric current. So, what does a light switch do? It acts as a mechanical gate. When you turn it off, the physical path is broken, and the flow of particles stops instantly. Electricity operates as a predictable, continuous physical system of pressure and flow. Now, imagine our smooth water pipe suddenly gets narrow and is filled with jagged rocks. The water struggles to get through, and the flow has to slow down and bunch up. Wires have internal obstacles that make it difficult for particles to pass. We call this resistance. This creates a balancing act. To get more flow, pump harder with more voltage, but add more obstacles, increasing resistance, and the flow slows down. In 1827, a physicist named George Simon Ohm figured out how to measure this relationship exactly. He proved the math connecting pressure, flow, and resistance, which we now call Ohm's law. These mathematical tools allow us to control and direct the flow of electricity, building specific paths to make it do exact jobs. To spin 3 water wheels, the simplest way is to put them in a row on one single pipe. This is a series circuit. It works until one wheel jams. Because they share a single path, one jam blocks the entire pipe. Everything stops. To fix this, we split the pipe into 3 separate pathways. Each branch gets a dedicated wheel. This is a parallel circuit. If one wheel is blocked, water simply bypasses it. Flow continues seamlessly down the open paths. By wiring our homes in parallel, we ensure that if a single light bulb burns out in the kitchen, the rest of the house stays bright. Think about the rocks in our narrow pipe. When water crashes through a highly resistant space, all that physical friction generates heat. The exact same thing happens in a wire. When millions of tiny particles squeeze through high-resistance metal, they rub against the material. The wire's temperature rapidly spikes. We harness this intentional friction every day. Inside a toaster, electricity is forced through exposed, high-resistance coils to generate the intense heat needed to cook your breakfast. If a wire can get incredibly hot without melting, the friction will eventually make it glow. That glowing obstacle is the heart of an incandescent light bulb. This intentional friction provides the heat for our kitchens and the light for our rooms. To figure out exactly how much total work a water park has accomplished by the end of the day, you calculate the sheer volume of water pushed through its pipes. In a circuit, we measure the total electrical energy consumed over time. We call this electric power, and it is measured in a unit called watts. That gray box attached to your house does exactly this. The meter tracks the total volume of electrical water you've pumped into your home over the month. By balancing these simple rules of pumps, pipes, and obstacles, we turn an invisible movement of particles into a reliable utility for every household.